Hi Andy, good morning. This is again Dr. C.H. Kiran Kumar dealing you the machine learning part. Today, in continuation of distance model machine learning, let us talk about KNN. KNN, nearest neighbors. No, before going to that, let us now discuss what is called, no, already discussed, but still just revise of what is called centroid, what is called medoid. What is called centroid and what is called medoid, right? Geometric centroid can be centroid exemplars. These two are called exemplars, my dear friends, exemplars. These exemplars define the neighbors. Now one exemplar is centroid. The centroid is generally, it is the geometric center. Geometric center. See, this is how it is designed. See, if you take all these points, no, the blue, the light green are the points here. And see, these are the points here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 points are here. So for these 16 points, if I calculate the centroid by just mean, by taking the mean, approximately it gives you the mean point here. So this is called median or centroid, whatever it is. This type of thing is called centroid. Centroid. Now medoid also can be done, but in general, medoid is applied where geometric median is not possible, but still it can be placed. Let us see the difference between these medoids and the centroids. Right, there's for a graph showing, see, data points, squared 2-norm centroid, mean, 2-norm centroid geometric median, and square 2-norm medoid, 2-norm medoid, and 1-norm medoid. Let us see this. Now, these are all data points. 1, 2, 3, 4, 5, 6, 7. There is a medoid outlier. And even these are called plus. Another plus, another plus. So there are around 10 data points here. Around 10 data points here. So among these 10 data points, right, square 2-norm centroid mean. This shows the mean of these centroids. This is centroid. This is centroid, my dear friends, and the neighbors are, see, this is one neighbor, this is the second neighbor, this is the third, fourth, fifth, maybe you can write sixth, seventh, something else. So this is the geometric median. This is the geometric median. Geometric median. And similarly, if you take 2-norm medoid, no, with another formula, if you take 2-norm medoid, this is the 2-norm medoid. Square 2-norm medoid. This is 2-norm medoid. This is the 2-norm medoid. And 1-norm medoid. This is 1-norm. So this is how you can have, if these are all our data points, centroid and medoid you can be given, see, something like this. Now we can definitely choose the neighbors. The neighbors. That is the use of basically centroid or medoid, right? A small data set of 10 points, which is with circles indicating centroids and squares indicating medoids for different distance metrics. Right, let us see now. Right. Now we can use this centroid or medoid methods by just defining some region boundary. Define some region boundary. That is, for example, if a medoid or a centroid is found here, then suppose if this is the centroid, then we can use radius. So radius, so that this is radius, and if I apply the radius here, now we can classify all a new set. This is all training data, my dear friends. This is all training data and new data. Suppose if a new data comes here, new data point comes here, we can definitely, if that data point lies in this circle, we can classify that of this class. Otherwise, we cannot classify that as this class. As simple as this. This type of this is how exemplars, the decision boundaries can be used. Hope you understood, my dear friends. Let me tell you again. See, if you take a centroid or medoid like this, you vary the radius. You take some radius, vary the radius so that, see, now you can definitely say how to classify the new data, as simple as this is how it is used. Now in general, how it is used, in general, the neighbor KNN, we are going to discuss what is called KNN, nearest neighbor. This is also one method. This is also a method. But generally, what we do is, we do here like this, nearest neighbors. Suppose if there is things like this, now if a point comes here, now how do we classify this, either plus or minus? Take nearest neighbors. How many nearest neighbors? How many nearest neighbors? This is the question. This is only called as KNN. How many? If K is 1, check only one neighbor, which is the nearest neighbor, and determine that class to the new class, new data point. If K is 2, then you have to take two nearest points, then you have to apply voting. After that, you classify the new data point as that particular class. If K is 3, then you have to find 3 data points, 3 nearest neighbors. This is how it goes. Let me have some theoretical part for this. Let us go for it. Once we have determined the exemplars, distance-based way to classify instances is by following a decision rule. If X is nearest to mu positive, then classify it as positive. Otherwise, as negative, as simple as this. If X is nearest to positive, then we classify it as positive. Otherwise, classify it as negative. Or equivalently, classify an instance to the class of the nearest exemplar. If we use Euclidean distance as our closeness measure, simply this is geometry tells us that we exactly have the same decision boundary as of linear thing. Right? See, this is what is exemplar theory in general? Why we are using exemplar? Exemplar theory is proposal to concerning the way human categorizes objects and ideas in psychology. Exemplar theory is relative to relative to humans thinking in psychology. Exemplar theories are nothing but memorization. You have to remember exemplar. You need not worry about exemplar. But the idea here is very simple, my dear friends. The simple thing is calculate. No, this is training data. You remember the training data. Get the new data point. Check the new data point, nearest exemplars, then apply the same class of that exemplar to the new data. As simple as this. This is what it is. No, right, anyhow. The basic linear classifier can be interpreted from distance-based perspective as constructing exemplars that minimize squared Euclidean distance within each class, and then applying the nearest exemplar decision rule for each point, for each training point. Construct exemplars that minimize squared Euclidean distance for within each class, and then apply the nearest exemplar decision rule. See, this is what it is, right? Increasing the number of exemplars further means that some of the regions are closed convex, giving rise to what is known as Voronoi tessellation. Since the number of classes is typically much lower than the number of exemplars, decision rules often take more than one nearest exemplar into account. This increases the number of decision regions further. Something like this. Regions are more. Now, Voronoi tessellation, right? Now, the most commonly used distance-based classifier is, it simply uses each training instance as an example. Consequently, training the classifier requires nothing more than memorizing the training data. See, we remember, you see, this is our training data. Training data has been saved. Now, if a new data point comes, no, you have remembered all existing training data, and now you apply the nearest neighbor classifier very simply. The extremely simple classifier is known as the nearest neighbor classifier. Its decision regions are made up of the cells of Voronoi tessellation with piecewise linear decision boundaries selected from Voronoi boundaries. Let us see, right? Voronoi tessellation, my dear friends. What are the properties of the nearest neighbor classifier? First, notice that unless the training set contains an identical instances from different classes, identical instances, we will be, no, unte, identical instances lekapothe. See, training set law, for example, this is the training set. For example, this is the training set. That is, no, for example, this is the training set. See, this is median, this is samyam, this is 2, if suppose. Now, all the points whose x value is less than 2 and whose y value is greater than 2 form a plus. Now, if our training data resembles the same, then we can easily separable. If in our training data, suppose if a minus comes here, then we may not be in a position to separate. But otherwise, we can easily separate. So we will be able to separate the classes perfectly on the training set. Unless, see, notice that unless the training set contains identical instances. Identical means for the same. ఒక్కసారేమో మైనస్ ఇస్తుంది ఫర్ ద సేమ్ డేటా సెట్, ఇంకొకసారేమో ప్లస్ ఇస్తుంది. అలాంటి కండిషన్స్ కనుక మన ట్రైనింగ్ సెట్ లో లేకపోతే then we will be able to separate the classes perfectly on the training data. This is very important, right? As we memorized all training examples, furthermore, by choosing the right example, we can more or less represent any decision boundary or at least an arbitrary close piecewise linear nearest neighbor classification approximation. See, either you can find the nearest or exactly the same class. This is called nearest neighbor. Let us say the nearest neighbor classifier has low bias but also high variance, my dear friends. It has got low bias but high variance. Move any of the exemplar spanning part of the decision boundary and you will also choose the boundary. This suggests a risk of overfitting. If the training data is limited, very small, noisier and unrepresentative. From an algorithmic point of view, the training the nearest neighbor classifier is very fast, taking only order of n time for sorting an exemplars. The downside is that classifying a single instance also takes order of n time, as the instance will need to be compared with every exemplar to determine which one of that is nearest. It is possible to reduce classification time at the expense of increased training time by storing the exemplars in a more elaborate data structure, but this tends to scale well to large number of features. When there are large number of features, it again goes back. Now, the thing is, you have to, whenever, training data is remembered here. Whenever a new data point comes, the new data point has to be checked with this, have to be checked with all exemplars, and then only you can find the nearest exemplar, nearest one. Of course, it takes only order of n time, but it has to be compared with every exemplar, determine which one of the one is nearest. So, can we reduce this? The answer is, some say yes. Elegante. Use another data structure in the exemplar itself. For every exemplar, you have to create another data structure called as, maybe if you remember that, so then it may be possible, but for number of features increase, if number of features gets increased, this also gets, the quality of this also gets, complexity of this also gets increased. So the nearest neighbor method can easily be applied to regression problems with a real value target variable. In fact, the method can be used to output text documents, images and videos also. It is also possible to output the exemplar itself instead of separate target, in which case we usually speak of nearest neighbor retrieval. Of course, we can only output targets stored in the exemplar database, but if we have a way of aggregating these, we can go beyond this restriction by applying k nearest neighbor method. Now, instead of checking with each, the distance, smallest distance and all, we can apply k nearest neighbor method. What is, in its simplest form, the k nearest neighbor classifier takes a vote between the k is greater than or equal to 1, nearest examples of the instance. See, nearest k is greater than or equal to 1. K is greater than or equal to 1 means, see this. This is how it is. K greater than or equal to 1, nearest examples, exemplars. All exemplars. This is all exemplars. All exemplars. All can be predict the majority class. Majority. Now you take the majority. That is called voting. We can easily turn this into probability estimator by returning the normalized class counts as probability distribution over classes. This is called voting. Hope you understood, my dear friend. So finally, the k nearest neighbor, the number of different predictions it can make initially increases with increasing of k. K 1, 2, 3. The number of predictions, the number of different predictions that can make initially increases, but then decreases again. This is the result theory result. Furthermore, we can say that the bias gets increased and the variance gets decreased with increase of k. But there is no easy, it is not easy to decide what value of k is appropriate on the given data set. So for which value of k, the prediction would be high. See, we cannot decide this. There is no, we cannot decide this. But of course, distance weighting to the votes. Distance weighting to the, that is, the closer an exemplar is to instance to be classified, the more its vote counts. Vote counts. See, that is called distance weighing. Distance weighing. So this is what k nearest neighbors. Now, if k nearest neighbor is used for regression problems, the obvious way to aggregate the predictions from k nearest neighbor is taking the mean value, which can again be distance weighted. Distance weighted, that is mean value. The mean. See, the distance. This would lend to the model additional predictive power by predicting values that are not observed among stored examples. So more generally, we can apply k-means to any learning problem where we have an appropriate aggregator for multiple target values. Slight variation in voting. So this is how k nearest neighbor regression can be used for regression problem. K nearest neighbors. Hope you understood, my dear friends. K nearest neighbor. See, we have we talked about what is called exemplar, what is called centroid, medoid, how centroid looks like in a space. Now after that we have what is exemplar, how exemplars, Voronoi tessellation, what is called Voronoi tessellation, and then nearest neighbor. What do you mean by nearest neighbor? And what is called k nearest neighbors? K1, what do you mean by K1? What do you mean by K2? K1 means k greater than, the simplest form. The k nearest neighbor classifier takes a vote between the k greater than or equal to 1 nearest examples of instance to be classified. See, something like this. So, right. So, hope you understood, right? And this is now how do we determine k? K can be 1 or 2 or 3 or 4 or 5, something like this. But k, it is observed that with increasing of k, so initially good predictions are coming, but then no, then no, after going to some extent, say 6 or 7, automatically the predictions are getting decreased. This is what the observed the right. The k nearest neighbor. This is called k nearest neighbor. Hope you understood. Thank you. Right. Next concept is called scatter matrix. Scatter matrix. What do you mean by scatter matrix? See, let us see. We only go with the definition today. Tomorrow we will explain all these things. A scatter matrix consists of several pairwise scatter plots. Pairwise scatter plots. Plot variables represented in a matrix format. Presented in a matrix format. This is called scatter matrix. It can be used to determine whether the variables are correlated and whether the correlation is positive or negative. This is how it is. Suppose we have, if we have 1, 2, 3, 4 different variables, different variables. Now, this is 1, this is 2, this is 3, this is 4, this is 1, this is 2, this is 3, this is 4. This is 1 versus 1. This is 1 versus 1. This is 1 versus 2. This is 1 versus 3. This is 1 versus 4. Something like this. 2 versus 1. 2 versus 2. 2 versus 3. Something like this. Pairwise. Pairwise scatter plots. Pairwise scatter plot. And in the form of a matrix. 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, something like that. Such form is called scatter matrix. Scatter matrix. Now it is easy to look at the pairs. Look at all pairs. So it will definitely give you the view, the exact view. Anyhow, we'll see. Now, given a data matrix X, the scatter matrix is the matrix S is equal to X minus 1 mu whole power T into X minus 1 mu. X minus 1 mu. This is also can be written as sigma I is equal to 1 to n xi minus mu whole power T into xi minus mu. Where mu is a row vector, a row vector containing column means, column 1 mean, column 2 mean, column 3 mean. The scatter X is defined as scat of X. Column, for each column is defined as sigma I is equal to 1 to n modulus of xi minus mu whole square. This is distance, which is equal to the trace of the scatter matrix, the sum of all its diagonal elements. This is the definition of scatter matrix. We will see now in the next class.